June 5, 1942. 16 kilometers north of Sevastopol, Crimean Peninsula. The earth itself seemed to hold its breath. Major Wilhelm Grimmeisen stood beside the most monstrous creation of artillery engineering the world had ever witnessed. Behind him, stretching nearly the length of 2 football fields, sat Schwerer Gustav, a railway gun so massive that its designers had to invent new mathematical formulas just to calculate the stresses on its barrel. The weapon towered 4 stories high. Its bore measured 31.5 inches across, wide enough for a man to crawl and inside. Let us know in the comments from where in the world you are watching from today. The complete assembly weighed 1,350 tons. Around him, 500 men of Heavy Artillery Unit E672 prepared for a moment 3 years in the making. Engineers checked hydraulic rams. Ammunition handlers positioned a 7-ton armor-piercing shell, a projectile that stood taller than 2 grown men. Krupp scientists consulted firing tables, their calculations accounting for variables no artilleryman had ever considered before. The curvature of the earth across a 29-mile arc, the microscopic expansion of steel under pressures that would shatter conventional artillery pieces like glass. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Gustav's barrel, 106 feet of forged Krupp steel, angled toward the Soviet fortifications that had defied conventional siege weapons for 7 months. Deep beneath Severnaya Bay, the Soviets had constructed an ammunition magazine 30 meters below sea level, protected by 10 meters of reinforced concrete. No weapon in the German arsenal could touch it, but Gustav wasn't standard artillery. Gustav was Hitler's answer to a fortress that refused to fall. The weapon existed because of a question asked 6 years earlier, March 1936, Essen, Germany. Adolf Hitler toured the Krupp steel works, walking past foundries that had forged German artillery since the Franco-Prussian War. Gustav Krupp von Bohlen und Halbach, the company's director, guided the Führer through workshops where workers shaped the instruments of war. Hitler stopped beside a scale model of the Maginot Line, 280 miles of interconnected defences, 140 artillery forts, 350 gun emplacements, 5,000 bunkers, 55 million tons of steel, and 1.5 million cubic meters of reinforced concrete, the most formidable defensive structure ever built. Hitler turned to Krupp with a question that would reshape artillery history. What would it take to destroy this? Krupp had an answer ready. His engineers had been studying the problem since 1934. The specifications were unprecedented. The gun would need to punch through 7 meters of reinforced concrete or 1 full meter of solid steel armor plate from beyond the range of French counter-battery fire. Erich Müller, head of Krupp's artillery development department, had calculated the requirements. A weapon with a caliber of approximately 80 centimeters, a projectile weighing 7 tons, a barrel 30 meters long, total weapon weight exceeding 1,000 tons, and because of that immense mass, the only way to make it mobile would be to mount it on specially reinforced railway tracks. Hitler gave his approval with one condition. The gun must be ready by spring 1940, in time for the invasion of France. By early 1937, the designs were complete. Krupp presented specifications for an 80-centimeter railway gun. The German Army High Command approved construction under the code name Implement D, Schwerer Gustav, Heavy Gustav. Named after Gustav Krupp himself, fabrication began in mid-1937 at Krupp facilities in Essen. From the outset, technical complications exceeded even the most pessimistic engineering estimates. The barrel presented the first major obstacle. No forge in Germany had ever attempted to shape steel components of this size and precision. The barrel consisted of 2 sections, each requiring individual forging, then precise joining with massive threaded connections. Any imperfection would cause catastrophic failure when 7 tons of shell met 4,630 pounds of propellant. Krupp metallurgists worked in uncharted territory. Standard steel alloys couldn't withstand the pressures. New formulas had to be developed, tested, adjusted. Each barrel blank took months to forge, weeks to cool, additional weeks to machine. The first attempts failed stress testing. Engineers returned to their calculations, modified the designs, began again. The carriage system presented equally complex challenges. Gustav's 1,350-ton weight had to be distributed across 2 parallel sets of railway tracks without crushing the rails or destabilizing the weapon during firing. Standard railway infrastructure would collapse instantly under such loading. Engineers designed a system of 8 bogies, massive wheeled assemblies each mounted on 2 parallel tracks. Each bogie required 5 axles, creating a total of 40 axles with 80 wheels to spread the enormous load across maximum surface area. Even then, standard railway tracks couldn't support the weight. Special reinforced rails had to be manufactured to Krupp's specifications, using steel alloys developed specifically for this application. The mathematics of load distribution alone required months of calculation. Engineers had to account for static loading when the gun sat at rest, dynamic loading when it moved along the tracks, and the enormous shock loading when it fired. Each shot generated recoil forces that would tear conventional artillery pieces from their mountings. The track system had to absorb these forces, distribute them safely, prevent catastrophic failure that would destroy the weapon and kill everyone nearby. The recoil system demanded innovations in hydraulic engineering that pushed beyond anything attempted previously. When Gustav fired, kinetic energy equivalent to a freight train hitting a wall at full speed had to be controlled, dampened, dissipated. Krupp engineers designed massive hydraulic cylinders capable of absorbing energies that conventional artillery couldn't imagine. The cylinders contained special hydraulic fluid developed specifically for extreme pressures and temperatures. The seals used materials that didn't exist in standard engineering applications. The entire system represented a masterpiece of mechanical design, created by engineers working at the absolute limits of what 1930s technology could accomplish. Loading mechanisms required mechanical ingenuity on an unprecedented scale. The 7-ton armor-piercing shell had to be lifted from railway cars, positioned behind the gun, hoisted nearly 4 stories to the firing deck, through a complex arrangement of cranes and lifting beams, then precisely aligned with the breech opening. The tolerances were microscopic relative to the component's size. Misalignment by even millimeters would prevent the shell from seating properly, causing catastrophic failure when the propellant ignited. A separate system handled the brass cartridge containing 4,630 pounds of propellant, lifting it up the opposite side of the gun, positioning it behind the shell. Both had to be loaded, the breech mechanism closed and sealed, the gun elevated to firing position, all without manual handling of components that would crush men like insects if anything failed. The breech mechanism alone represented years of design work. It had to seal completely against pressures that would blow conventional breech blocks through the rear of the gun. The 20-ton breech block slid into position on massive rails, locked in place with huge screw threads, sealed with a brass obturation case that expanded under pressure to create a perfect seal. The mechanism had to work reliably after repeated firing cycles that subjected every component to shock, heat, and stress beyond normal engineering parameters. As 1937 became 1938 and 1938 became 1939, the original spring 1940 deadline became increasingly unrealistic. Every component pushed the limits of German industrial capacity. By late 1939, Krupp constructed a test model at Hillersleben Proving Ground. On a cold morning, the test model fired its first shot. A 7-ton armor-piercing shell, launched at high elevation toward concrete targets constructed to Maginot Line specifications. The shell struck and penetrated 7 full meters of reinforced concrete, exactly as specified. Follow-up tests confirmed penetration through 1 meter of solid steel armor plate. The fundamental physics worked. Gustav could accomplish what Hitler wanted. In early 1941, Alfred Krupp personally hosted Hitler and Albert Speer, the Minister for Armaments, at the Rügenwalder Proving Ground on the Baltic coast for formal acceptance trials. The location had been chosen carefully. Remote enough for secrecy, large enough for the gun's assembly and testing, with terrain suitable for constructing targets that replicated Maginot Line fortifications. German construction crews had spent weeks building concrete bunkers to exact specifications, creating miniature fortresses for Gustav to demonstrate its capability against. Hitler arrived expecting disappointment. The gun had missed its critical deadline by an entire year. The Battle of France, the very campaign Gustav was designed to support, had been won in May 1940 without the weapon's participation. German forces had simply outflanked the Maginot Line through Belgium, rendering the massive fortifications irrelevant through maneuver rather than firepower. The Wehrmacht had demonstrated that even the strongest fixed defences could be defeated through superior tactics and operational art. Many in the military high command questioned whether Gustav represented wasted effort, resources that should have been allocated to conventional weapons that could be mass-produced and deployed rapidly. The gun existed as a solution to a problem that had already been solved through different means. But when Hitler saw the assembled weapon for the first time, doubt transformed into obsession. The gun stretched across the landscape like an industrial cathedral, a monument to German engineering prowess. 155 feet long from the front of the barrel to the rear of the railway carriage, 38 feet high, tall as a 4-story building, 23 feet wide, requiring special track spacing to accommodate its massive structure. The barrel alone weighed over 100 tons, more than an entire Tiger tank. The breech mechanism, a complex arrangement of gears, rams, and hydraulic systems, resembled factory machinery more than a weapon, an industrial installation dedicated solely to loading and firing shells of unprecedented size. The firing demonstration that followed confirmed the weapon's devastating potential beyond anything Hitler had imagined. A 7-ton armor-piercing shell, loaded over the course of 30 meticulous minutes by crews who had practiced the procedure hundreds of times. The shell hoisted to the firing deck, aligned precisely, loaded into the breech. The propellant cartridge following, positioned, sealed. The gun elevated to maximum angle, its hydraulic systems straining against the enormous weight. The command to fire echoed across the proving ground. The roar was beyond description, a sound that seemed to compress the air itself, felt in bones and organs before it registered in ears. The muzzle flash, brilliant even in daylight, a miniature sun erupting from the barrel's end. The recoil, absorbed by hydraulic systems that flexed and compressed, dissipating energy that would have torn any conventional gun from its mounting. And downrange, 23 miles away, target bunkers built to the most stringent military specifications simply ceasing to exist. Concrete walls 3 meters thick, reinforced with steel bars, designed to withstand direct hits from the heaviest conventional artillery, disintegrating under the impact. The crater left behind measured 12 meters across and 12 meters deep, a wound in the earth itself. Hitler declared the weapon magnificent, a testament to German industrial supremacy. He commanded that the largest shells, the 7-ton armor-piercing projectiles, could only be fired at his personal discretion, requiring his explicit authorization for each shot. But another question remained, a question that would haunt the weapon's entire operational existence. What targets existed anywhere in the world that required a gun this size, this expensive, this complex to operate? By early 1942, only one target remained worthy of Gustav's capabilities: Sevastopol, the fortress city on the Crimean Peninsula that had resisted German siege since November 1941. Sevastopol represented everything the Wehrmacht found frustrating about siege warfare. Coastal batteries protected the harbour. Underground facilities stored supplies beyond the reach of bombers. The Black Sea Fleet ensured continuous resupply. The 11th Army had laid siege for 7 months, yet the city held. In February 1942, Heavy Artillery Unit E672 received orders to mobilize. Gustav would go to war. The weapon travelled in 25 railway cars, a train 1.5 kilometres long. Behind came additional trains carrying 500 personnel, ammunition, tools, and 4 diesel-electric locomotives designed specifically to manoeuvre Gustav. Engineers selected a location 16 kilometres north of Sevastopol, German construction units began the most labor-intensive artillery preparation in military history. A special railway spur had to be built. At the end, engineers constructed 4 semicircular tracks where Gustav would traverse to aim. The gun had no built-in traverse mechanism. To aim left or right, the entire weapon had to be moved along curved tracks. The preparation required 2,000 to 4,500 men, working for 5 weeks. Infantry provided security, flak batteries protected the position, construction units laid track, engineers surveyed firing solutions. By early May, the site was ready. 250 men began assembling the weapon, working in carefully orchestrated shifts around the clock. 54 hours. 3 full days of precise, dangerous work. Moving components weighing dozens of tons into exact alignment, connecting systems, testing mechanisms. The breech ring, 20 tons of precisely machined steel, had to be fitted to the barrel's rear and locked with a massive junction nut that required special tools to tighten. The barrel sections, each transported separately to meet railway weight restrictions, required the gantry cranes to lift and position with tolerances measured in fractions of millimeters. The front half of the barrel had to insert perfectly into the jacket housing. The rear half had to mate with the front, locked together with enormous threaded connections. The assembled barrel, over 30 meters of forged steel weighing more than 100 tons, then had to be lifted as a complete unit and lowered onto the gun carriage, positioned onto the cradle assembly that would allow elevation changes. Any error during assembly would cause catastrophic failure when the gun fired. At best, the shell would miss its target wildly, wasting ammunition that cost more than most families earned in years. At worst, the barrel would explode, transforming 100 tons of steel into shrapnel that would kill everyone within hundreds of meters. Krupp engineers supervised every step personally, checking each connection, verifying each measurement, testing each system before proceeding. They had designed the weapon. They understood the stresses. They knew precisely where failures would occur if assembly tolerances weren't maintained absolutely. Teams of technicians checked and rechecked each connection, each hydraulic line, each mechanical linkage, each electrical circuit. The gun represented 3 years of design work and 7 million Reichsmarks of investment for the second unit alone. One moment of carelessness, one overlooked defect, one improperly tightened bolt, would destroy everything. On June 5, 1942, after 5 weeks of preparation and 3 days of assembly, Schwerer Gustav was ready to fire in combat for the first time. 500 men stood at their positions. Major Grimmeisen gave the order. Fire. The earth trembled. A roar unlike anything the soldiers had experienced rolled across the landscape. The muzzle flash illuminated the darkness. Shockwaves rippled through the ground, felt by troops 16 kilometers away. Downrange, 7 tons of steel traveling at 720 meters per second fell toward coastal battery positions. The shell's impact created a crater 12 meters wide and 12 meters deep. The coastal battery position simply ceased to exist. The gun crew worked through their loading sequence, 20 to 45 minutes per round. Loading crews hoisted shells up one side, while propellant cartridges ascended the other. A hydraulic ram pushed the shell into the breech. When everything aligned perfectly, the command came: fire. Through June 5th, Gustav fired 14 rounds. The coastal batteries, Fort Stalin, each target received methodical attention. The shells demolished targets conventional artillery couldn't touch. Concrete walls 3 meters thick shattered. Underground chambers collapsed. June 6th brought Gustav's defining moment, the target called White Cliff. Soviet engineers had constructed an underground ammunition magazine beneath Severnaya Bay. The facility sat 30 meters below sea level, buried in bedrock, protected by 10 meters of reinforced concrete. Nothing in the German arsenal could reach it. Fire control officers calculated the trajectory, maximum elevation. The shell would fall nearly vertically. The gun elevated to 48 degrees. 500 men held their positions. This shot represented everything Gustav was designed to accomplish. The command came: fire. The shell arced high over Sevastopol. It struck the earth above the ammunition depot, and kept going, through 10 meters of concrete, through solid bedrock, into the magazine itself, buried 98 feet below the surface. The detonation was unlike anything Sevastopol had experienced. The earth itself seemed to rupture. A massive explosion erupted from underground, throwing concrete fragments hundreds of meters into the air. Shock waves radiated through the ground. A mushroom cloud rose above the bay, visible across the entire peninsula. If you find this story engaging, when German observers please take a moment to subscribe and enable notifications. They found a crater 50 meters across. Producing in-depth. The entire facility had been obliterated. Over 1,000 tons of ammunition had detonated simultaneously. The destruction validated everything Krupp engineers had calculated. But the reality on the ground told a more complex story. Through June and early July, Gustav fired 48 rounds total. Each shot required 30 to 45 minutes to prepare. The ammunition alone presented continuous challenges. Each shell weighed 4.8 to 7 tons. A single error would cause catastrophic accidents. The barrel wear exceeded predictions. Gustav's barrel had been designed for approximately 300 rounds before requiring refitting, but the extreme pressures and temperatures degraded the rifling far faster than calculations suggested. After only 48 rounds at Sevastopol, accuracy had declined noticeably. The rifling grooves showed significant erosion. Heat stress had created microscopic fractures in the steel. Krupp engineers examining the barrel declared it worn beyond acceptable tolerances. Replacing the barrel required nearly as much effort as initial assembly. The massive barrel sections had to be disconnected, lowered by the gantry cranes, loaded onto railway cars. The spare barrel, transported with the guns specifically for this eventuality, was unpacked, inspected, hoisted into position. The process consumed 2 full days, 2 days when Gustav sat silent, while conventional artillery continued pounding Soviet positions. The original barrel was shipped back to Essen for relining, a process that would take months. At the Krupp factories, metallurgists would examine the wear patterns, determine what had caused the accelerated degradation, modify the steel composition if possible. The barrel would be rebored, new rifling cut, the entire surface machined to restore tolerances. Then, tested again at proving grounds before being deemed ready for combat use. The process cost nearly as much as manufacturing a new barrel. The resource consumption staggered Wehrmacht logistics officers attempting to coordinate supplies for the entire 11th Army. 4,000 men, directly or indirectly, supported Gustav's operations. 500 operated the gun itself, manning loading positions, fire control stations, maintenance duties. 2,000 to 4,500 had prepared the firing position, laying track, digging earthworks, constructing the infrastructure. 2 flak battalions provided air defense, their anti-aircraft guns positioned to protect the massive artillery piece from Soviet air attack. Infantry companies secured the perimeter, preventing partisan infiltration or sabotage. Medical personnel stood ready to treat casualties from the inevitable accidents when handling components this massive. Every day Gustav remained operational. It consumed resources at rates that would have supplied multiple conventional artillery batteries. Ammunition transport alone required dedicated railway capacity. Each shell needed its own specially constructed wooden crate for protection during transport. Each propellant cartridge came in brass cases that had to be manufactured to precise specifications. The specialized diesel-electric locomotives consumed fuel at prodigious rates. Spare parts inventory included components that existed nowhere else in the Wehrmacht supply system, custom-manufactured items that couldn't be requisitioned through normal channels. German field commanders questioned the allocation with increasing frustration. At Sevastopol, 785 German and 112 Romanian medium and heavy guns participated in the siege, representing the concentrated artillery power of an entire army group. These conventional weapons, ranging from 105mm field guns to 420mm howitzers, fired tens of thousands of shells daily. They could shift fire rapidly between targets, respond to infantry requests for support within minutes, saturate defensive positions with sustained bombardment. 3 Karlgerät 600mm self-propelled mortars accompanied the siege forces, firing 2-ton shells that produced destruction nearly comparable to Gustav's, with far greater mobility and at a fraction of the operational cost. The Luftwaffe's 8th Air Corps flew 23,751 sorties in June alone, dropping 20,528 tons of bombs on Soviet positions, fortifications, and supply lines. In this overwhelming context of firepower delivery, Gustav's 48 shells represented a tiny fraction of the total ordnance delivered against Sevastopol. Yes, the 7-ton shells destroyed specific hardened targets that conventional weapons couldn't penetrate. Yes, the White Cliff ammunition depot explosion was spectacular and undeniably effective. But when Wehrmacht operations staff conducted after-action analysis, uncomfortable questions emerged. Did the destruction of one underground magazine, however impressive the explosion, actually justify the enormous resources consumed? Could those same resources, if allocated to conventional artillery batteries, fighters, or additional infantry divisions, have produced greater tactical advantage? Would Sevastopol have fallen faster with more conventional firepower, rather than this single superweapon that fired slowly, required extraordinary support, and could only engage carefully selected targets? By early July, Sevastopol fell. 30,000 tons of artillery ammunition had reduced the city to ruins. Gustav's role remained debated. Wehrmacht reports credited the gun with destroying critical targets, but operational analysis suggested the city would have fallen regardless. Several weeks after Sevastopol fell, Gustav Krupp personally presented the first gun to Hitler as a gift. But what came next revealed the weapon's fundamental limitation. There were no more targets worthy of Gustav. The gun was dismantled and transported to the northern sector, where preparations began for an assault on Leningrad. Construction units built firing positions 30 kilometers from the city. Gustav was reassembled, tested, made ready. 500 men stood at their positions. The attack was cancelled. Soviet forces launched counter-offensives that threatened German positions. Gustav, which required weeks to position, couldn't adapt to fluid battlefield conditions. The gun sat idle through the winter of 1942 and 43, consuming resources without firing a single round. The second gun, Dora, experienced even briefer service. Deployed west of Stalingrad in late August 1942, positioned 15 kilometers from the city. By September 13th, Dora was ready to fire. Then Soviet forces threatened encirclement. Dora was hastily withdrawn, never having fired a combat round from that position. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By 1943, German military circumstances had changed dramatically. Resources were desperately needed for mobile weapons. Static superweapons served no purpose in a war that had become a struggle for survival. Albert Speer cancelled the third variant, Lange Gustav, in November 1944. The incomplete components were scrapped. As Allied armies advanced toward Germany from both east and west in early 1945, Wehrmacht units received urgent orders to destroy any advanced equipment that might fall into enemy hands. Gustav was moved from its position near Leningrad back toward Germany through increasingly dangerous territory. Soviet partisans attacked German railway transport regularly. Allied aircraft controlled the skies. The journey consumed weeks, with the convoy moving at night, hiding during daylight. On April 14, 1945, with American forces less than 1 day's march away, German engineers received final orders to destroy the gun approximately 50 kilometers southwest of Chemnitz, in a forest north of Auerbach. They placed demolition charges at critical points. The barrel, the breech mechanism, the carriage structure. When the charges detonated, 3 years of design work and millions of Reichsmarks shattered into scrap metal scattered across a German forest floor. American troops discovered the ruins on April 22nd. Photographs show soldiers beside the destroyed barrel. Dora met a similar end. deliberately destroyed on April 19th at Grafenwöhr. Erich Müller, the engineer who designed Gustav, faced post-war justice. At Nuremberg, he and Alfred Krupp were sentenced to 12 years imprisonment for crimes against humanity. Krupp received pardon after 3 years. Müller was released after 4 years. The technical achievement represented by Gustav remains undisputed. The weapon accomplished exactly what it was designed to do. The engineering required to create a gun this size represented breakthrough achievements, but the strategic value remained questionable. Gustav existed because Hitler wanted symbols of Nazi superiority. The gun made impressive propaganda. It demonstrated that German industry could accomplish impossible feats, yet it consumed resources desperately needed elsewhere. The contrast with more practical weapons proved telling. German 88mm guns destroyed thousands of Allied tanks throughout the war. U-boat campaigns nearly strangled British supply lines. These weapons influenced the war's outcome far more than any superweapon. Gustav represented the opposite philosophy: uniqueness over mass production, symbolic impact over practical utility, engineering achievement for its own sake rather than operational requirements. The accuracy problems became apparent as data was analyzed. Of 48 rounds fired at Sevastopol, only 10 fell within 60 meters of their targets. The most inaccurate shot missed by 740 meters. For a weapon this expensive, such accuracy was unacceptable. The limitations stemmed from multiple factors. The enormous size made the weapon sensitive to environmental conditions. Wind affected trajectory. Temperature variations changed air density. The gun's weight caused ground settlement. Barrel wear affected rifling. Fire control calculations couldn't account for all variables, affecting a 7-ton projectile traveling 29 miles. The psychological impact on Soviet defenders was real but difficult to quantify. Soldiers who survived described the terror of massive explosions, but psychological impact alone doesn't win battles. Sevastopol fell because the Wehrmacht deployed overwhelming conventional force, not because Gustav frightened defenders. Soviet specialists who examined Gustav's remains studied the design carefully. Their conclusion: while technically impressive, the weapon had no practical military value. Soviet doctrine emphasized mobile artillery and rapid deployment. Gustav contradicted every principle of effective artillery employment. American ordnance specialists reached similar conclusions. The United States had built Little David, a 914mm test mortar, but it remained a test device, never seeing combat. American doctrine prioritized weapons that could be mass-produced and flexibly employed. The resource allocation question haunted post-war analysis. How many Tiger tanks could have been built with Gustav steel? How many conventional artillery pieces? Resources allocated to prestige projects were resources unavailable for practical weapons. The story of Schwerer Gustav reveals a truth about military technology that remains relevant. Innovation doesn't necessarily produce advantage. Engineering achievement doesn't automatically translate to battlefield success. The most impressive weapon isn't always the most effective weapon. Gustav represented the peak of artillery gigantism: 80 centimeters, 7 tons, 1,350 tons, total weight, the ultimate expression of bigger is better philosophy. But the Eastern Front had evolved beyond static siege warfare. Blitzkrieg emphasized speed, mobility, combined arms coordination. The operational tempo demanded weapons that could redeploy in hours, not weeks. Gustav belonged to a previous era. The Maginot Line had been defeated through maneuver, not penetration. German forces simply went around it. The lesson applied to Gustav itself. The weapon could destroy any fortification, but it couldn't adapt to changing situations. Its power was rendered useless by inflexibility. Gustav also revealed the danger of allowing political considerations to drive military procurement. Hitler's fascination with superweapons created pressure to develop Gustav regardless of operational requirements. Wehrmacht commanders who questioned the weapon risked Hitler's displeasure. This pattern repeated throughout German weapons development. The Maus super-heavy tank, weighing 188 tons. The V-weapons program diverting resources to ballistic missiles. Each project diverted resources from practical needs. Gustav fit this pattern perfectly. Spectacular engineering, limited military value, resources consumed that could have been used elsewhere. The gun existed because Hitler wanted it, not because Wehrmacht commanders needed it. The soldiers and engineers who worked on Gustav understood these contradictions. Many took pride in solving unprecedented technical challenges. The loading system alone represented mechanical engineering mastery, the barrel metallurgy, the hydraulic systems. These achievements deserved respect, but professional pride couldn't change operational reality. Gustav fired fewer than 100 rounds in combat throughout its service life. The thousands of man-hours produced minimal tactical impact. The question of Gustav's accuracy became increasingly relevant. 10 rounds within 60 meters of target, out of 48 fired. 740 meters maximum miss distance. For conventional artillery, such accuracy would be unacceptable. The defensive requirements further limited utility. The gun's size made it visible from great distances. The two flak battalions, assigned, represented hundreds of soldiers dedicated solely to defending one artillery piece. The vulnerability to air attack meant Gustav could only operate under German air superiority. When the Luftwaffe controlled the skies, the gun could function. When Soviet aircraft contested superiority, Gustav became a liability. The comparison with Allied super-heavy weapons proved instructive. British and American forces concluded that conventional weapons in large quantities provided better results than superweapons in small quantities. Soviet artillery doctrine evolved in the opposite direction. Soviet forces emphasized massed artillery, hundreds of guns concentrated at breakthrough points. The Katyusha multiple rocket launcher exemplified this philosophy. Simple, mass-producible, mobile, devastating in large numbers. The contrast symbolized different military philosophies. Germany built one gun firing 7-ton shells. The Soviet Union built thousands of launchers. Germany pursued engineering excellence. The Soviet Union pursued mass production. The Eastern Front's outcome suggested which philosophy proved more effective. Gustav's legacy in artillery development was essentially negative. Post-war planners concluded that super-heavy static artillery had no place in modern warfare. Nuclear weapons rendered conventional artillery obsolete for strategic destruction. Precision-guided munitions allowed small warheads to achieve destruction that previously required massive shells. Modern artillery emphasizes the opposite of Gustav's characteristics. Lightweight for air transportability, allowing guns to be deployed anywhere within hours. Rapid deployment capability, with complete firing batteries operational within minutes of arrival. Extended range through rocket assistance and guided projectiles that can strike targets 50 to 70 kilometers distant with precision Gustav never achieved. Automation to reduce crew requirements from hundreds to fewer than 10. Digital fire control systems that calculate solutions in seconds rather than hours. The entire philosophy moved decisively away from massive static weapons toward light, mobile, precise systems that could be mass-produced and deployed globally. The engineering knowledge gained from Gustav did influence post-war developments in unexpected ways, though not in artillery. Stress analysis techniques developed for calculating loads on the gun's barrel contributed to understanding large structure mechanics used in bridge construction, skyscraper design, and pressure vessel manufacturing. Hydraulic system designs influenced industrial machinery, particularly in heavy manufacturing and mining equipment, where massive forces must be controlled precisely. The fire control calculations advanced ballistic science and computational mathematics, contributing to trajectory analysis used in early space programs. The metallurgy research into high-strength steel alloys found applications in commercial and industrial uses far removed from weapons. But these contributions came incidentally, as byproducts of solving problems unique to Gustav. They could have been achieved through less expensive research programs focused on civilian applications rather than military superweapons. Krupp Company survived the war, though the family's leadership faced serious war crimes prosecution at Nuremberg. The company underwent Allied-mandated transformation into a peaceful industrial concern. Its factories converted from manufacturing weapons to producing steel products, machinery, and commercial equipment for reconstruction. The expertise that had designed Gustav, the engineers who had solved unprecedented technical challenges, found application in rebuilding Germany's destroyed infrastructure, bridge construction, industrial machinery, commercial vehicles. The knowledge remained valuable, but it served peaceful purposes rather than destruction. Former weapons engineers designed cranes, machine tools, construction equipment. Their skills, developed creating instruments of war, contributed to post-war recovery and economic development. But the human cost remained part of history. The company employed slave labor during the war. Resources used to build Gustav came from a system based on exploitation. Erich Müller's post-war sentence reflected this reality. He had solved engineering problems considered impossible, but he had done so in service of Nazi Germany. Technical brilliance didn't absolve moral responsibility. Gustav's story illustrates the danger of rationalization. The weapon existed because talented engineers agreed to solve problems posed by a criminal regime. Technical work isn't morally neutral when performed in service of evil purposes. The gun also demonstrated the limits of technical solutions to strategic problems. Germany's fundamental challenge was resource disadvantage. The Allies outproduced Germany in every category. Germany couldn't match Allied production capacity. Gustav represented the wrong approach. Invest enormous resources in one impressive weapon rather than producing many adequate weapons. Pursue technical perfection rather than operational effectiveness. This approach guaranteed failure. The final irony was that Gustav succeeded technically while failing strategically. The gun accomplished what it was designed to accomplish. The engineering worked. The weapon functioned as intended. Yet all this success added up to strategic insignificance. This outcome contains lessons for military procurement in any era. Impressive capability doesn't guarantee utility. Technical sophistication can reduce operational effectiveness. Individual weapon performance matters less than system performance. Resources have opportunity costs. Gustav remains in historical memory as a symbol of engineering taken to extremes. The largest mobile artillery piece ever built. Museum displays feature Gustav shells next to tanks to illustrate their enormous size. The Imperial War Museum in London has an 800mm shell in its collection. Perhaps the most appropriate memorial to Gustav is the lesson it teaches. Military power comes not from individual weapon impressiveness, but from effective integration toward operational objectives. The most spectacular weapon isn't automatically the most effective weapon. Modern militaries have internalized these lessons. Procurement emphasizes operational requirements over technical possibilities. Cost-effectiveness analyses compare weapons based on tactical value. Mobility, maintainability, and mass producibility receive priority over raw power. Yet the temptation remains. Every generation sees proposals for superweapons promising miraculous capabilities: lasers, electromagnetic railguns, directed energy weapons. Each promises advantages similar to what Gustav was supposed to provide. The question planners must ask is whether these modern superweapons will avoid Gustav's fate. Will they provide capability justifying their cost? Will they integrate into operational doctrine? Can they be produced in sufficient quantities? If the answers suggest another Gustav, resources should be allocated elsewhere. The Schwerer Gustav story ends not with its destruction in April 1945, but with the understanding it provides. Understanding about the relationship between technology and military effectiveness, about the danger of political considerations driving procurement, about the importance of operational flexibility over raw capability. The gun fired fewer than 100 rounds in combat. It existed for barely 3 years as an operational weapon. It accomplished tasks conventional artillery couldn't perform, yet accomplished nothing that changed the war's outcome. It represented engineering triumph and strategic failure. When German engineers destroyed Gustav in April 1945, they ended the operational history of the largest mobile artillery piece ever built. But they couldn't destroy the questions the weapon raised. Questions about technological capability versus military effectiveness. Questions about resource allocation. Questions about pursuing impressive capabilities rather than useful ones. The ruins discovered by American forces represented more than destroyed artillery. They represented the end point of a particular philosophy, the belief that bigger was necessarily better. That technical sophistication automatically produced military advantage. The ruins demonstrated where that philosophy led. Gustav's barrel, shattered by demolition charges, couldn't fire again, but the weapon's history continues to teach. The lessons apply beyond artillery, beyond World War II, beyond any specific technology. They speak to fundamental questions about how military organizations should allocate resources, evaluate weapon proposals, and decide what capabilities actually matter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.